What's up, everybody? It's Dan from SageMathTutoring.com, and we have a test review for a geometry test for a student of mine who has a test tomorrow. And I just want to go over a couple problems right now and just make sure that the concepts are clear for my student. So we're just going to kind of walk through all of these problems right away. So let's begin right now. Looking at problem number 15, write a conditional statement from each Venn diagram. So my student is really good at realizing that the hypothesis is the small thing and the conclusion is the large thing. So with regards to problem number 15, we could say, if it is Monday, then it's a weekday. All right, weekday. So my handwriting is not that good, but we're just going to go with it. Problem number 16, if it is lichen, then it is fungi. All right. Worst handwriting ever, but that's fine. Determine if each conditional is true. If false, give a counterexample. If two angles are adjacent, then they have a common ray. That is true. Okay, so what that means is it's two angles, like we have this blue angle and we have this green angle, and they both share a common ray. That would be the one that's in the middle. Okay, so it turns out that that's actually true. That is a true conditional. Problem number 18. If you multiply two irrational numbers, the product is irrational. So that's actually not true. And the reason is because an example of an irrational number would be radical 2. And another example might be something like radical 32. Those are irrational numbers. However, if you multiply them together, it would be radical 64 because it's 2 times 32 is 64, and the square root of 64 is actually 8. And that right there is rational, whereas the original two things that we multiplied together are irrational. So this is false. And the quote unquote counterexample, this is the counterexample. Radical 2 times radical 32, well, that gives us radical 64, which turns into 8. So that would be a counterexample. All right, so for my student who's watching, just remember, counterexample is a statement or an example that would prove the original statement to be false. Okay, so this would be one of those. Problem number 19, my student did really good with converse, inverse, and contrapositive. So for problem number 19, if x is a right angle, then the measure of angle x is 90. So the converse would be to reverse it. If the measure of angle x is 90, then x is a right angle. The inverse is if x is not a right angle, then the measure of x is not 90. And if it's contrapositive, it would be if the measure of angle x is not 90, then angle x is not a right angle. Okay, so that's the case there. So if we try to figure out what the truth value is of each, well, let's start with the original. If x is a right angle, then the measure of angle x is 90. That's true. If the measure of angle x is 90, then x is a right angle. That's the inverse. Well, that's actually true as well. So that would make it a biconditional, by the way. The fact that you could do the converse and it's still true, that means it's biconditional. The inverse is if x is not a right angle, then the measure of angle x is not 90. That actually is true as well. And the contrapositive says if the measure of angle x is not 90, then angle x is not a right angle. That would be true as well. All right, so they're all true, actually. Looking at problem number 20, if x is a whole number, then x equals 2. Okay, so that's false, first of all. All right, now the converse is if x equals 2, then x is a whole number. Well, that's actually true. If x equals 2, then x is a whole number. So that's actually true. Looking at the inverse, if x is not a whole number, then x is not equal to 2. That's actually true. If x is not a whole number, then it's definitely not going to be 2. So we know that that's definitely true. And then finally, the contrapositive says if x is not equal to 2, then x is not a whole number. That's false because it's possible for x to be, if x is not equal to 2, well, x might be 3, and that would not be a whole number. So that would be a counterexample. So the idea that if x is not 2, then x is not a whole number, well, that right there is false because there's plenty of counterexamples to that. So hopefully that is helpful. Now, I do believe my student said that we don't need to cover 2.3, so that's okay. So for problem number 27, we want to know, determine if a true biconditional can be written from each conditional statement. If not, give a counterexample. So we know that a true biconditional can be written if the original thing is true and the converse is true. Now, clearly the original is what they wrote. That's in the red box. Now, the converse, I think my student understands, would be if x equals 5 halves, then 3 minus 2x over 5 does indeed equal 2. So in order for the true biconditional to be the case, this red box would have to be true and the blue writing would have to be true. Okay. Now, one thing we can do actually is immediately investigate the red box original statement. One way of doing that is we could actually solve for x. So we have 3 minus 2x equals 2. We could subtract 3 from both sides. That would give us negative 2x over 5 equals negative 1. We could then multiply both sides by 5, right? And that would give us negative 2x equals negative 5. We could then divide both sides by negative 2. That would give us x equals 5 over 2. And that indeed is true, right? That's what they're saying. So we know that the original statement is true. So the red box statement is true. But now the question is the blue writing statement, the converse, is that actually true as well? Well, one way of checking that is they're saying x equals 5 halves, then this thing must be true. Well, we could always substitute 5 halves into x. So instead of x, I'm going to write 5 over 2 over 5. And that's going to equal 2. Now, if we simplify that, it's going to be 10 over 2 in the numerator over 5. And we'll see if that equals 2. So 3 minus 10 over 2 is just 5. So that would be 3 minus 5. So that's 3 minus 5 over 5, and that equals 2. And 5 over 5 is just 1, so that would be 3 minus 1 equals 2. And that is definitely true. 2 equals 2. So we're good to go. So that would be yes. We checked both the original statement, which is in red, and we checked the blue statement, which is the converse. And they both turned out to be true. So therefore, a true biconditional could be written. Okay, so that is problem number 27. Looking at problem number 28. If x is less than 0, then the value of x to the 4th power is positive, okay? So that's the original statement, which I'll do in red right here. Now, let's get clear on the converse, though. The converse of that would be to write that in the reverse, right? And we're going to do that right now. So if we write that in the reverse, then that would say if x to the 4th is positive, then x is less than 0. So let's investigate the red box original statement. So if x is less than 0, then the value of x to the negative 4 is positive. Well, actually, if x is less than 0, then x is negative. And if you have a negative number, like negative 1 or something, and we raise that to the 4th power, well, that would indeed be a positive one, because it would be a negative number times another negative number times another negative number times another negative number. And that would be positive. And the reason is because these two would be positive. These two would be positive. And a positive times a positive is a positive. So we already know the red box scenario is true. But what about the blue? What about the converse? If x to the 4th power is positive, then x is less than 2. Well, that's actually not true. And the reason is because, x to the 4th, a prime example would be 16. And that's 2 times 2 times 2 times 2. Well, that would give me 16. But as you can see, these are positive numbers, whereas according to the blue box statement, if x to the 4th is positive, then x has to be less than 0, x has to be negative. Well, we just presented a counterexample where x was positive, and a positive number to the 4th power is 16, is a positive number. So therefore, we presented a counterexample that essentially proves that x does not need to be negative necessarily if x to the 4th is positive. Okay, so hopefully that makes sense. All right, looking at problem number 29, if a segment has endpoints 1 comma 5 and negative 3 comma 1, then its midpoint is negative 1 comma 3. The midpoint formula is x1 plus x2 divided by 2 comma y1 plus y2 divided by 2. And in this case, we could call 1 comma 5 and negative 3 comma 1 x1 y1. This could be x2 y2, and an example, or the midpoint of this should be 1 plus negative 3 over 2, and we would have 5 plus 1 over 2, and in that case it would be negative 2 over 2 and 6 over 2, and that would be negative 1 comma 3 as the midpoint, and that does indeed check out here. So we know that the original is true. However, I'm already seeing that the converse is not necessarily true, because if we said if a midpoint is negative 1 comma 3, then the endpoints have to be 1 comma 5 and negative 3 comma 1. Well, there could be a counterexample to that. For example, negative 1 comma 3 is right here. What if we just had the point negative 2 comma, negative 2 comma 3, and what if we also had another point of, we could say 0 comma 3 right here? Well, this black dot right here, which is at negative 1 comma 3, well, that is the midpoint between these two endpoints, but the two red endpoints here are not the same as 1 comma 5 and negative 3 comma 1. So here's an example of how that black dot, the negative 1 comma 3, could be the midpoint of other endpoints. So therefore the converse is not true. Therefore we could say that this biconditional, there can be no true biconditional that could be written here. Okay, so we just presented a counterexample. Problem number 30. If the measure of one angle of a triangle is 90, then the triangle is a right triangle. So that actually is true. All it takes for a triangle to be a right triangle is if one of the angles is 90, and the converse would actually be true as well. If a triangle is a right angle, then by definition, then the measure of one angle in the triangle happens to be 90. Okay, so I don't feel like I need to write that. That's sort of something that you can just see. Complete each statement to form a true biconditional. Two angles are blank if and only if the sum of their measures is 90. Okay, so that would be complementary. Okay, so that could also be a vocab word that my student should know. Two angles are complementary if and only if the sum of their measures is 90. Problem number 32. X to the third power is greater than 0 only if x is positive. Okay, and the reason for that is because if x was negative, any negative number to the third power, well, that's going to give you a negative number. Okay, anytime you have a negative number raised to the third power, that's going to give you a negative result. So x cubed being positive only would be true if the original x happens to be a positive number. All right, problem number 33. Trey can travel 100 miles in less than 2 hours if and only if his average speed is, okay, so average speed is derived from this formula: rate times time equals distance. Now, rate is the speed, so it makes sense that the rate should be distance divided by time, okay? So the average speed, 100 miles in less than 2 hours, well, we could figure out, well, what is that speed? Well, that would be 100 miles and less than 2 hours. So that average speed has to be 50 miles per hour or more. You can think about it. So you could say 50 miles per hour or more. Okay. So that's that. Problem number, let's see, 34. The area of a square is equal to side squared if and only if the perimeter of the square is equal to, okay, so if a square has an area of side squared, that means that the side length is S, and this is S, and the area would be S times S. That would only be true if the perimeter was S plus S plus S plus S. So we could say that would only be true if the perimeter is 4S. Hopefully that makes sense. All right, problem number 35. Solve each equation and write a justification for each step. So the justifications are going to be given by all this stuff. We have the addition property of equality that basically says if A equals B, then A plus C must equal B plus C. The subtraction property of equality says that if A equals B, then A minus C must therefore equal B minus C. The multiplication property of equality says that if A equals B, then A times C must equal B times C. The division property of equality says that if A equals B, then A divided by C equals B divided by C. And the substitution property of equality says that if A equals B, then A could be substituted for B or B for A in any equation or expression. Okay, so looking at problem number 35, we have M divided by 5 plus 3 equals negative 4.5. So the first thing we should do is subtract 3 from both sides. Now that's clearly going to be the subtraction property of equality. So that's what you should write if it's the test. Okay, and then we have M over negative 5 equals negative 4.5 minus 3, which is negative 7.5. At that point, we can then multiply both sides by negative 5. And I think you understand that's probably going to be, well, it's definitely going to be the multiplication property of equality. In doing so, these cancel, and we end up with M equals negative 7.5 times negative 5, which is going to be 37.5. Okay, so that's that one. Problem number 36, and once again, that was the multiplication property of equality. Problem number 36, we have negative 47 equals 3x minus 59. We could add 59 to both sides, and that would be 12. Now that's the addition property of inequality, okay? And then you could divide both sides by 3. That's the division property of equality, and then you would have x equals 4, all right? So that's that one. Okay, so looking at problem number 37, identify the property that justifies each statement. Okay, so this has to do with other properties that my student needs to know, and they are as follows. That would be these. So for my student who's watching this, you must know the reflexive, you must know the symmetric, and you must know the transitive property. All right, now this says A plus B equals A plus B. Now that's clearly going to be the reflexive. Anytime you say something equals itself, that's the reflexive property, so that's reflexive. This says if angle RST is congruent to angle ABC, then it must be true that angle ABC is congruent to RST. Well, that's the symmetric. Anytime you see symmetric, it says if A equals B, then the reverse must be true. B must equal A. Well, isn't that what this is? If this thing is congruent to that, then that must be congruent to this. So my student must be familiar with reflexive and symmetric. And then there's this one, 2x equals 9 and y equals 9. So 2x equals y. Okay, so that is kind of a toss-up between the substitution property. Substitution property says if A equals B, then A can be substituted for B in any equation or expression. So we see for sure that anytime you see 9, you could replace it with a y. Anytime we see 9, we could replace it with a y, which means that this 9 could be replaced with y, and that's what they're saying right here. So that's the substitution property. I feel like that could also be transitive, but I think the teacher would be fine with you just saying that that's the substitution property of equality, all right? Use the indicated property to complete each statement. Reflexive property of congruent. Figure A, B, C, D. Well, according to the reflexive, everything is equal to itself. So that means that's going to be A, B, C, D right there, right? Symmetric property of equality. If the measure of angle 2 is equal to the measure of angle 5, well, symmetric says if A equals B, then B equals A. So that means you're just going to rewrite the same thing, except in a different order. You're going to say, then it must be true that the measure of angle 5 is equal to the measure of angle 2. All right? So that's the symmetric. Transitive property. If AB is congruent to CD and AB is congruent to EF. So that would be then CD has to be congruent to EF. Okay, so that's transitive. I mean, in a way, it's kind of weird. It's like if AB is congruent to CD, and we also know that AB is congruent to EF. So by the transitive property, which is here, then these two things must also be congruent. Now, I actually feel like that could be substitution as well. Transitive and substitution are very similar, okay? Kim borrowed money at an annual simple interest rate of 6% to buy a car. How much did she borrow if she paid $4,200 in interest over a life of a 4-year loan? Solve the equation interest equals PRT for P and justify each step. Okay, so we're just going to solve that. We're going to write the equation here. Interest equals principal times rate times time. Now the principal is the original amount. So let's see. She borrowed money, 6%. She paid 4,200 in interest. So that's the I, 4,200. We know the R is 6%, and you should represent that as a decimal. And that's after 4 years. T is 4 years. So we're trying to figure out what the P is, what the principal is. So what we could do here is we can multiply 0.06 times 4, and that is 0.24. And at that point, what we can do is take advantage of the division property of inequality by dividing both sides by 0.24. That would cancel this. That's the division property of equality. And 4,200 divided by 0.24 is 17500. All right, so that's the answer to that one. Okay, geometric proof. Write a justification for each step. Let's see. These are examples, right? Okay, problem number 44. Write a justification for each step given that angle 1 and angle 2 are complementary. All right, so we already know that they're equal to 90 degrees, right? Because they're complementary if you add them together. And angle 1 is congruent to angle 3. So if angle 1 is congruent to angle 3, then these two guys have the same measure. We also know that angle 1 and 2 are complementary. So when you add the red angle 1 to the blue angle 2, then you're going to get 90 degrees if you add those degree measurements up. So write a justification for each step. So this is basically a 2-column proof. So the justification for number 1, angle 1 and 2 are complementary. Okay, so that's a given. All right. Measure of angle 1 plus the measure of angle 2 equals 90. That's the definition of complementary angles. All right. Of complementary. Problem number 3. Angle 1 is congruent to angle 3. Well, that's given. That was given in the problem, right? Problem number 4. The measure of angle 1 equals the measure of angle 3. That's the definition of congruent. Okay. Problem number 5. The measure of angle 3 plus the measure of angle 2 equals 90. Okay, I would say that's substitution. All right, and I'm going to explain that. So, we've already established that the measure of angle 1 plus the measure of angle 2 equals 90. Then we said, oh, by the way, the measure of angle 1 equals the measure of angle 3. So what that means is since the measure of angle 1 is equal to the measure of angle 3, that means you could substitute this measure of angle 3 in for the measure of angle 1. You could replace that with the measure of angle 3, and that is exactly what they did on this green box line. What they did in the green box line is they replaced that measure of angle 1 with the measure of angle 3. Once again, measure of angle 1 plus the measure of angle 2 equals 90. We know that the measure of angle 1 equals the measure of angle 3. That means we could replace the measure of angle 1 with the measure of angle 3, which is exactly what we did right here, and that is the substitution property of equality, all right? And then at that point, the measure of angle 3 and the measure of angle 2 are complementary, and that's the definition of complementary. All right, so definition of complementary, because basically if two angles add up to 90, then it means that they have to be complementary by the definition of complementary. All right, so the proofs are kind of weird. It takes a little getting used to. 45, fill in the blanks to complete the two-column proof. So given TU is congruent to UV, so they use these tick marks to help us see that. We want to prove that SU, which is this segment right here, plus TU, which is this segment right here, is equal to SV, which is this whole thing. All right. So we're establishing that this tick mark and this tick mark are the same length. So we want to prove that the green part plus the blue part must equal this entire red part. So TU is congruent to UV, that's given, right? Now the next thing says it's the definition of congruent segments. So anytime they say definition of congruent segments, that means look at the thing that came before, and basically you might have to just replace that congruent symbol with an equal sign. So you could say TU, the measure of TU is equal to UV. Okay, that's the actual length of TU is equal to the length of UV. That's the definition of congruent segments. Now they say the segment addition postulate. So that means that when you add two segments, they equal each other. Now what we're looking for is that SU plus UV equals SV. Okay, so I'm going to write that here. SU plus UV equals SV. All right, that is the segment addition postulate. This green part plus this little guy is equal to the whole thing. All right. And then if you look very closely, what they did is they then swapped out the UV with the TU. You can replace the UV with the TU because we've already established that TU equals UV. So this is the substitution property of equality. All right, so hopefully that makes sense. We established that SU plus UV equals SV by the segment addition postulate, and we can swap out that UV with the TU because we've already established that TU equals UV, and that is the substitution property of equality. And this is what they wanted us to prove at the end of the day. All right, so that's that. Find the value of each variable. So these two angles are going to add up to 180. So therefore we have z minus 2 plus 2 plus 7z equals 180. Now how do I know that they add up to 180? Because they're a linear pair. There's this sort of straight line here, and then you have the green angle and you have the yellow angle here. It's obvious that the green angle plus the yellow angle is going to add up to the straight line, which is 180. So therefore it makes sense that the green angle, which is z minus 2, plus the yellow angle, which is 2 plus 7z, if you add it all up, it's going to be 180. So at that point, you can combine like terms. Z plus 7z is 8z. These would cancel. Next thing you know, you have 180. 180 divided by 8 is 22.5. All right. This one right here is such that this angle plus this angle clearly equals 90. So it's going to be 3x plus 2x plus 5, and that equals 90. That's going to be 5x plus 5 equals 90. Subtracting 5 from both sides, we have 5x equals 85. Dividing both sides by 5, we're going to have 17. All right, unless I made a careless mistake, but that's that. Okay, getting into flowchart proofs. Use the given plan to write each of the following. So they're giving us a plan, which is really cool. Now, the first thing I'm seeing even before we dive in is that they want us to use something called the congruent complements theorem and the common angles theorem. So let's get clear about what both of those are before we begin. So the congruent complements theorem says if two angles are complementary to the same angle, then they are congruent. So in other words, if this angle and angle 5, if angle 4 and angle 5 are complementary, meaning they add up to 90, And it's the case that angle 6 and angle 5 add up to 90 because they're complementary. Then it must be the case that angle 4 is congruent to angle 6, meaning they're the same measure. Okay, so that's the congruent complements theorem. So we just want to make sure we're aware of that. Now let's look at the common angles. Now it can be very easy to get lost in this stuff, but we're going to take it step by step. The measure of angle VZW, okay, that's this thing. VZW is equal to the measure of angle XZY, which is right here, okay? Then the measure of angle, I'll color code this with green, the measure of angle VZX, that's this guy, has to be equal to the measure, this purple, measure of angle WZY. So that's this. So let me say that again. If these two blue guys are equal, then this green guy and the purple guy have to also be equal. All right. Now, in a way, they're just saying the same thing in reverse. This is the converse of what they just said here. Okay. So this is nothing more than the converse of what we just said. But let me say it one more time. All right, and I'm gonna get rid of this. This is we're gonna use their diagram. If this blue guy equals this little blue guy, then this big green guy has to equal the purple guy. That's the common angles theorem. All right. So let's see what they're talking about here. They're saying ADE and DAE are complementary. So I'm going to color code it. ADE is the red. That's this. And DAE, which I'll make green, DAE, that's this guy. They're complementary. So apparently the red plus the green equals 90. We also know that ADE and BAC are complementary. BAC. Now BAC, which I'll do purple, BAC is right here. So just based off of that information, ADE and the purple, the red and the purple are also complementary. The red and the purple are also complementary. So the red and the green are complementary, and the red and the purple are complementary. Now already I can tell, because of the congruent complements theorem, that if the red and the green are complementary, and the red and the purple are complementary, then what that means is the green and the purple have to be congruent. That's literally the congruent complements theorem. If this and that are complementary and this and that are complementary, then these two must be equal to each other. Now, what do they want us to prove? They want us to prove that DAC, ultimately they want us to prove that the yellow angle right here is congruent to BAE. BAE. So I'm going to make that the weird color, BAE. That's this color here. That is not too bright. We're going to make a different color. Let's see. What if we went with, we'll go with this bluish kind of thing. So we'll use that. That's BAE. We want to prove that this yellow marker is congruent to this blue one. All right, now clearly that's going to be a common angle scenario, right? So let's dive in. Use the congruent complements theorem to show that DAE is congruent to BAC. All right, so that's going to be the first thing. Now, if we're going to do a flowchart proof, we want to immediately start writing the givens down, okay? So the givens are angle ADE and angle DAE complementary. We also have another given. That's given. We also have a complementary that says, or another given rather, that says that angle ADE and BAC C complementary. That's also given. So we are just going to follow their plan. Use the congruent complements theorem to show that DAE is congruent to BAC. So I feel like we can probably draw just a single arrow between these. And seeing as how both of those are true, we immediately know that angle DAE is congruent to angle BAC, and that is a result of the congruent complement theorem. Congruent complement theorem. And in my opinion, based off of literally the common angles theorem that says if blue equals blue, then green equals purple, I actually feel like we're ready to actually hit this with the final statement, which I'm going to draw over here. It's kind of ugly looking, but we can hit them with the final statement where we literally say angle DAC is congruent to angle BAE. Now, once again, DAC is the yellow. That's congruent to this blue. And that's because we already established that the green is equal to the purple. Okay, so the green is equal to the purple. We established that this green is congruent with the purple, right? The green is congruent with the purple, so therefore the yellow must be congruent with this blue here, which is this statement here. Okay, I'll keep it color-coded. So the yellow guy has to be congruent with the blue guy. All right, this yellow has to be congruent with the blue. And then we would be done because that right there is the common angles theorem. Okay, so kind of messy, kind of weird. It definitely requires a knowledge of congruent complements theorem and common angles theorem. Okay, so hopefully that's clear. Problem number 50. Find the value of each variable and name the theorem that justifies the answer. So I can already tell that this is going to be a vertical angle scenario, which is based on this, and this is going to be a linear pair postulate, which is based on this. So before we even worry about this, let's make sure we're clear on these, okay? So for my student watching, sounds like you should know vertical angles and linear pairs as well. Now, vertical angle says that any time you cross two lines together, the angles that are on opposite sides are going to be congruent to each other. They're going to be equal measures. So that applies to 1 and 3. 1 and 3 are clearly congruent to each other, but 2 and 4 are congruent to each other, okay? So let's just be very clear. 1 and 3 are congruent to each other, and 2 and 4 are congruent to each other. 1 and 3 are the blue angles, and 2 and 4 are different angles and the green ones. Okay, so the blue guys are equal to each other and the green guys are equal to each other. That's the vertical angles congruence theorem. The linear pair postulate says that if 1 and 2 form a linear pair, meaning if these guys share a side, share a ray, and the other rays are opposite rays, like this, forming a straight line, then we know that the measure of angle 1 plus the measure of angle 2 equals 180. This measure plus this measure equals 180. That's the linear pair postulate, okay? So that's going to come into play for problem number 51, it looks like, all right? So for problem number 50, because these are vertical angles, because they're vertical angles, we know that they're equal to each other. So we have 135 can therefore equal 3W, right? So we could divide both sides by 3, and that would give us 45. All right, so W equals 45 there, unless I made a mistake. I don't think so. 3 times 4 is 12. Right. 3 times 5. Yeah. Okay, so that is due to the vertical angles congruence theorem. All right. This one right here is such that we know that if this is 2x, see the single rainbow there? That means that this is also 2x degrees. And we know based off of the linear pair postulate that this angle plus this angle add up to 180. Well, it's the same thing. This angle plus this angle add up to 180. So we can say 2x plus 2x equals 180. 2x plus 2x is 4x equals 180. And dividing 180 by 4 would give us 45. So it turns out that's 45 as well. Okay. So long story short, you are going to need to know vertical angles congruence theorem and the linear pair postulate. Okay, looking at this, find the next item in each pattern. Okay, so clearly that's going to be a little red dot down here. That's inductive reasoning. 405 to 135 to 45 to 15. 15 times 3 gives us 45. 45 times 3 gives us 135. 135 times 3, I believe that's going to give us 405. Yes, so it's going to be 15 divided by 3. It's going to give us 5. All right. Complete the conjecture. The sum of two even numbers, well, that's going to be even. Show that the conjecture all complementary angles are adjacent is false by finding a counterexample. Okay, here's a counterexample. You have 45 degrees here, here's an angle, and here's another 45-degree angle. They're both complementary in the sense that they add up to 90, but they're not adjacent. Look, this angle is all the way over here, this angle is all the way over here. They're not adjacent. Identify the hypothesis conclusion of the conditional statement. The show is canceled if it rains. My student's really good at this. The hypothesis is the thing that comes after the word if, so that's P, and the show is canceled is Q. Write a conditional statement from the sentence parallel lines do not intersect. So I'm not going to write that down. I would say if lines are parallel, then they don't intersect. If lines are parallel, then they don't intersect. Determine if each conditional is true. If false, give a counterexample. If two lines intersect, they form four right angles. No, that's not true because these, clearly, that's not a right angle, 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 right? So that's a counterexample. If a number is divisible by 10, then it's also divisible by 5. Well, that is true because if a number is divisible by 10, it's divisible by 5 times 2, which means that 5 is a factor of that number. That means it's also divisible by 5 as well, okay? So to say that a number is divisible by 10, like 20 divided by 10, that is to say that it's 20 divided by 5 times 2. So therefore that 20 is being divided by that 5 as well. Use a conditional. If you live in the United States, then you live in Kentucky. Write the indicated type of statement and determine its truth value. So if you live in the United States, then you live in Kentucky. So the converse would be if you live in Kentucky, then you live in the United States. So that would be true, right? The inverse is if you don't live in the United States, then you don't live in Kentucky. Well, that's true. Counterpositive is if you don't live in Kentucky, then you don't live in the United States. Well, that's false. Determine if the following conjecture is valid under the law of detachment. Given, if it is colder than 50 degrees Fahrenheit, Tom wears a sweater. If it is 46 degrees Fahrenheit today, conjecture, Tom is wearing a sweater. Okay, so the law of detachment says that, number one, in order for it to be in mathematical logic, the law of detachment says that if the following two statements are true, then we could derive the third statement. So the first statement is if P, then Q. Second statement is P is true. So therefore we can derive that Q is true. All right. So basically the law of detachment says given it is colder than 50 degrees, if it is colder than 50 degrees, then Tom wears a sweater. So P is it's colder than 50 degrees, Tom wears a sweater. So P is it's colder than 50 degrees, Tom wears a sweater. By the way, it's 46 degrees actually right now. Well, that's colder than 50 degrees, so therefore it is valid to say that Tom is wearing a sweater. Okay, so that makes sense. All right, law of syllogism. Given if a figure is a square, then it's a quadrilateral. If the figure is a quadrilateral, then it's a polygon. Figure ABCD is a square. Okay, law of syllogism is a little bit different. That says that the following. It says that if P, then Q, and then we could say if Q, then something else, and then we could derive the fact that if P, then something else. Okay, so if P, then Q, if this thing means that thing and that thing means this thing, then the original thing means the last thing. So we can draw a conclusion about the given information. If a figure is a square, that's P, then it is a quadrilateral. If a figure is a quadrilateral, then it's a polygon. Figure ABCD is a square. Okay, so that statement has nothing to do with what we just said. Okay, this is a whole nother thing out of left field. So we don't have enough information to say that ABCD is a square. Here's what we can say. If a figure is a square, then it's a quadrilateral. If it's a quadrilateral, then it's a polygon. What we could say is that if a figure is a square, therefore it's a polygon. That's what we could say by the law of syllogism, not this. Problem number 14, write the conditional statement in the converse within the biconditional. Chad will work on Saturday if and only if he gets paid overtime. So the moment you see if and only if, that means it's biconditional, and that means you could keep it in the same order, and then you could reverse it to the converse. So the original statement would be Chad will work on Saturday if he gets paid overtime. And the other way of saying is if Chad gets paid overtime, then he will work on Saturday. Okay, so you just switch the order. Determine if the biconditional B is the midpoint of AC if and only if AB and BC is true. So we have AC here. Let's put B in the middle, and apparently according to them, this is equal to that. Okay, well that is true. Okay, that is true. In that B is the midpoint. That is the definition of a midpoint. The definition of a midpoint, it is that point that would cut this AC in half. And clearly if AB equals BC, then it's cutting it in half. All right, problem number 16. Solve each equation, justify each step. Okay, so for problem number 16, 8 minus 5s equals 1. We can subtract 8 from both sides by the subtraction property of equality. That would be -7. We can divide both sides by -5. That's going to be 7 over 5. That's the division property of equality. I feel like I don't need to do these because my student probably would be just fine with that. Okay, identify the property that justifies each statement. So 2x equals y equals 7, then 2x equals 7. That's transitive. If a equals b and b equals c, then a equals c. It's the exact same thing. If 2x equals y and y equals 7, then 2x equals 7. That's transitive. Problem number 20, this thing equals itself. Well, that's reflexive. This thing equals itself. If x is congruent to p and p is congruent to d, then x congruent to d. Once again, that is transitive. If a equals b and b equals c, then a equals c. If st is congruent to xy, then xy has to be congruent to st. That's the symmetric property. If a equals b, then b equals a. You just switch the order of those things. All right, so hopefully that makes sense. Use the given plan to write a proof in each format. Okay, so given ABC, I'm just going to do a 2-column. I'm going to trust that my student knows how to convert a 2-column into a paragraph and a flowchart proof, but I only have time for the 2-column proof right now. So we have statements and we have reasons. Okay. Now before we begin, let's kind of wrap our head around what's going on. Given AFB is congruent to EFD, okay, they kind of labeled that for us. We want to prove that FB bisects AFC. Okay, FB, we want to prove that FB, which is in blue, bisects AFC. AFC. All right. So that one's not going to be too hard because right here we can see that this rainbow angle is congruent to this rainbow, this arc right here. is congruent to this one. We also know by vertical angles that this one has to be the same as well. And the moment we prove that this green angle is the same as this angle right here, then we know that the blue thing is bisecting the red thing, because that's what it means to bisect, is that you're cutting it in half and these two things are equal to each other. All right, so hopefully that makes sense. Let's see. Since the vertical angles are congruent, EFD is congruent to, right, exactly. Use transitive property to conclude that AFB is congruent to BFC. Right, okay. So first things first, write the givens. We have angle AFB is congruent to angle EFD. That's given, okay? Now to be clear, that's just saying that this rainbow angle is the same as that rainbow angle. All right, let me just erase this. Since vertical angles are congruent, EFD is congruent to BFC. So I'm going to color code that. What they're saying is that this angle, which is this, is congruent to the red angle, which is this, okay? So we could say angle EFD, which I'll keep in blue, is congruent to the red angle, which is angle BFC. Now that is because of vertical angles, okay? So we've established that. Now, if you look at what we've created, we said AFB is congruent to EFD. And by the way, EFD is congruent to BFC. So doesn't it therefore make sense that angle AFB has to also be congruent to BFC, and that is the transitive. That's the transitive property. Okay. So what we've established is that AFB, which is this guy, is congruent to BFC, which is this red one right here. And then we can literally say, we can hit it with the final move, which is that ray FB bisects angle AFC, and that's due to the definition of angle bisector. Okay, that's the definition of angle bisector. So we've established that this angle equals this angle, which means that this ray has to be cutting the larger angle in half. Okay, so I'll say it again. We have this yellow angle and we have this red thing. Now we're trying to prove that this red thing cuts the yellow angle perfectly in half. Well, we established that this angle is equal to this angle, which means the red thing cuts the yellow angle in half. We established that the one angle is equal to the other angle, which means that FB does indeed cut the yellow angle in half, which is the definition of angle bisector, okay? So hopefully that makes sense. Okay, quick review of this stuff. Linear pair theorem that basically says that if you have a linear pair, this thing plus this thing equals 180. Right angle congruence theorem. That means that if you have a right angle and a right angle over here, then they're both congruent to each other. Congruent supplements theorem. That means that if you have an angle like this that's supplementary with this angle is supplementary with the green angle, and if you have another angle that's supplementary with the green angle, then these two angles must equal each other. If blue is supplementary with green and black is supplementary with green, then green must be congruent with blue. Same thing with complements. Imagine if blue is complementary with green and black is complementary with green, then black must be congruent to blue. Vertical angles says that if you draw two lines that intersect like that, then the two blue guys have to be congruent with each other and the two red guys have to be congruent with each other. Okay, the rest of it is down here. So addition property of equality. If A equals B, then A plus C equals B plus C, meaning you can add C to both sides. Subtraction property of equality. If A equals B, then A minus C equals B minus C. In other words, you could subtract C from both sides. multiplication property of equality. If A equals B, then A times C equals B times C. In other words, you could multiply C times both sides. Division property of equality. That means that if A equals B, then A divided by C is equal to B divided by C. In other words, you could divide both sides by C. Substitution property. If A equals B, that means that you can substitute A in for B for any equation or expression. Okay, that's substitution. Reflexive property. That's right here. That basically says every entity equals itself. Every entity equals itself. Every entity equals itself. Reflexive property. If A equals B, then B, oh, that's reflexive. I just said reflexive. Symmetric. If A equals B, then B equals A. You just switch the order by which you mention that. If AB equals CD, well, guess what? CD equals AB. That's symmetric. Transitive. If A equals B and B equals C, then A equals C. In other words, you have B as the connecting link, and then if B is the connecting link, then these two guys also have to equal each other, which is what that says. And then finally, distributive properties. So we didn't really talk about that, but we're going to talk about it right now. That basically says that if you have A times the quantity of B plus C, I'm sure my student has some experience recognizing that you could always distribute that, and that equals AB plus AC, all right? Similarly, if you have A times B minus C, well, it's going to be the exact same, AB minus AC, all right, as a result of distribution. So that's the distributive property. Anyway, a lot of information in this video. Hopefully this is helpful. Good luck to my student, and I will talk to you all later.